All right, we are going to go to R to finish up chapter 5. So I'm going to use the cancer data set we've seen before to look at testing for normality in a population based on some sample data. So I'm going to go over three different main ways. Well, descriptive statistic, Shapiro-Wilks test, histograms, and QQ plots. So we're going to do this for two different variables in the cancer data set. So I'm going to use four different packages here. Tidyverse for general usage, Haven to read in an SPSS dataset, Furniture to do some descriptive statistics perhaps, and the Psych package for doing other describe functions. So this data set, I've cleaned it up. I can't get it to show correctly, so we'll switch right here. So the first thing when you're looking at normality of a population, the variable in a population, judging from a sample, the first thing you can do are calculate summary statistics, and the psych describe function is handy for that. Now I have selected only two variables out of my data set here. I'm selecting age and the total oral condition at week 4 in the study. So these two variables. So this psych describe by default calculates a lot of descriptive statistics, and two of them it calculates are skewness and kurtosis. Now, skewness and kurtosis can be used to judge normality as a descriptive statistic, but tests directly on them or guidelines for how big or too small is on these numbers are kind of weak. You might see some people quoting some citations about how big or too small for skewness and kurtosis is normal enough. I don't really subscribe to any of them, but it is something you can report. So the age variable, the skewness is about negative 0.3 and the kurtosis is really close to 0. So that's not too wild, although it's hard to know what wild is. Now, I want to compare that to this oral condition at week 4. It's got a slightly smaller skewness in the opposite direction, but its kurtosis is much bigger. Now, alone, these numbers of skewness and kurtosis are descriptive, but they're not really great on guidance for making a decision. So the next thing I'm going to show you how to do is testing normality directly, as in getting an inferential p-value out of it. So let's start with age. In our population, we want to know, is age normally distributed? And we can set up a hypothesis test to do that. For the Shapiro-Wilks test, the null hypothesis is always nothing's going on. So the null hypothesis for Shapiro-Wilks test is that the variable does follow the normal distribution. There's nothing wonky going on. It's fine, it's normal. So the null hypothesis is that age follows the normal distribution. The alternative hypothesis is not so much. There's something going wonky. So there is some evidence, or there's evidence that their age will not be following the normal distribution. Now, running the Shapiro-Wilks test is fairly easy in R. It has 3 steps. We always start with the name of the data set, then we have to pull out the variable we want to investigate, and then run Shapiro-Wilks test on it. Now, we've never seen the pull command before. This is new, and the Shapiro-Wilks command is new. The pulling of a variable, that's coming from the dplyr package, but the Shapiro-Wilks test comes out of base R. So this is what the code would look like. We always start with the name of the data set. Here it's called cancer clean. And then we pipe it into our step of pulling out the variable we care about. Now, I've highlighted in yellow, the variable name we care about here is age. So this is the code for checking normality in the age variable. Start with the name of the data set and then pipe it into dplyr :pull and then parentheses the name of the variable age. And then we pipe it into the last thing, Shapiro.test. And the parentheses for the Shapiro-Wilks test are empty. That's all the code. Now, over here, I have some other comments. When we have that hashtag or that ampersand, no, it's not ampersand, it's the pound sign, sorry. Everything after that is just text that the R is going to ignore. That's just comments. So if we run this code, we will get output that looks like this. The output tells us that it's Shapiro-Wilks normality test, and it tells us 2 numbers. The W is the test statistic, and then the p-value. I don't want you to worry about the W statistic. It's just a number. We're just going to let it be, and then the p-value. So when you would report this, a big p-value says fail to reject the null. And a small value, smaller than alpha 0.05, tells us we will reject the null. Now, that in and of itself is not a conclusion. Fail to reject or reject the null are not conclusions. So we have to go back up to what was our null hypothesis. Now, this p-value is not significant because it's much bigger than a 0.05. In fact, it's almost as big as it can get. The biggest a p-value can get is 1. It's 0.9. That's pretty close. So this is no evidence against the null. So this is no evidence that age does not follow the normal distribution. So our conclusion for this test, one way to write it, would be that the Shapiro-Wilks test on this sample provides no evidence that the distribution of age in the population is not normally distributed. Now, I know this is a double negative. It needs to be a double negative. There's no evidence it is not normal, which in turn means we can treat it as if it is normally distributed, but we need to be careful about accepting the null. We never want to accept that it's normally distributed. We are going to default, we are going to go with that, but our claim needs to be that there's no evidence that it's not normally distributed. And then APA would have us write the test statistic and the p-value at the end of the sentence separated with commas, not with parentheses. Now the W should be italicized and the p-value should be italicized. It's not here. I'm sorry. This p-value should be italicized. Again, that's strictly the APA guidelines. I will tell you that every single journal and every single department in school says that they follow APA, and then they all do their own things. So no guarantees there. Okay, so this was for the age variable. Now let's do this for let's look at the plots. So 4 different ways that you can look at normality. 1, you can look at the skewness and kurtosis numbers. I would definitely report them. You can run a Shapiro-Wilks test that may or may not give you evidence against normality. The third thing is plots. Now we've already seen making a histogram. You start with the name of the data set as always, and then you pipe it into ggplot. And in the aesthetics, you tell it the variable you care about, which this is age. Now we use pipes to connect steps until we hit ggplot. Once we get into ggplot, we add layers. So the layer we would add would be histogram. And this one defaulted to way too many bins, so I changed the bin width to be 5-year gaps so that it looked more reasonable. So looking at this histogram, is it a perfect bell curve? No. But is it roughly normal-ish? That's a judgment call you have to make. Another plot we can make is called a QQ plot, and this is for quantile plot, or sometimes it's called the normal quantile plot. And this one is another way of looking at normality. And the syntax is very similar. We start with the name of the data set, and then we pipe it into ggplot. The difference comes in the aesthetics. Instead of just saying the name of the variable, we have to say sample equals the name of the variable to denote that this is sample data. And then the layer we add is geomqq. And this will make a plot that has dots on it. If your distribution is perfectly normal, you will have a perfectly straight line of plot points in a 45-degree line. Perfectly straight. Now, is our distribution perfectly normal? Not perfectly, but it is fairly symmetrical, fairly unimodal, fairly bellish shaped, and so we get a fairly straight line. Now, this is definitely a judgment call, and when you start out, there's a lot of fuzzy middle ground. But I will tell you from experience, this is fairly normal. Now, because of Shapiro-Wilks says there's no evidence it's not normal. When we looked at the descriptives, it was slightly skewed negative and almost no kurtosis. If we look at the picture, notice how it's slightly skewed negative, and then the kurtosis is fairly bell-shaped. It's okay. So this variable age is fairly normally distributed. And the evidence I use is the numbers of skewness and kurtosis, Shapiro-Wilks test, and the histogram and QQ plots. Now, to show the difference, let's look at the other variable. Let's look at the week 4 oral condition variable. So we're asking the same thing. Is there evidence that total oral condition at week 2 is normally distributed in the population? And we have to make that judgment call based on just the sample we have available. always Shapiro-Wilks test has a null hypothesis, nothing going on. The null hypothesis is nothing wonky going on. It is normally distributed. Then the alternative says, something's going on. It's not normal. Again, the code, we start with the name of the data set, and then we pipe it in to dplyr pull to pull the variable we care about out. This time we're going to pull out the variable total CW4 for the total oral condition at week 4 and pipe that into Shapiro-Wilks. Now this time, when we run Shapiro-Wilks, our p-value is small. Small as in comparison to alpha equals 0.05. Our p-value is less than 0.05. So this is evidence against the null. So this is evidence against normality. So the way we would write it up is Shapiro-Wilks test on this sample does provide evidence that the distribution of total oral condition at week 4 in the population is not normally distributed. Again, with our test statistic W, don't worry about what that means, and our p-value. Again, for APA, for test statistics, you want 2 numbers after the decimal, and if we'd have a 0 in front of the decimal in this case. In p-values, we want 3 numbers after the decimal and no 0 in front of the decimal. Okay, so here Shapiro-Wilks says, looking kind of wonky. This is not normal. Let's look at the plots. Notice in the histogram, that's not very normal. It's very skewed. And if you look at the QQ plot, notice if you were to make a line out of those points, it would not be very straight. It would have an S bend to it. So this is an example of a non-normal distribution. Again, let's look at the picture. So here's fairly normal-ish, fairly straight line on the QQ plot, fairly bell-shaped in the histogram, versus not normal. We've got skewness obvious in the histogram and very clear S shape in the QQ plot. Again, we'll do lots of these as we go forward so that you can get more of a feel for what's normal and not normal, but we can also always have this clear-cut Shapiro-Wilks test. Now, I'm not a huge fan of the Shapiro-Wilks test because it tends to be oversensitive in big samples and undersensitive in small samples. And that's why most statisticians would prefer to see a plot. But I think it's one of the situations when you're checking for normality, you want to have multiple sources. Skewness and kurtosis, numbers, Shapiro-Wilks test, and pictures as in the histogram and the QQ plot. And all together you can get a bigger picture if a variable looks normal-ish or looks non-normal-ish.